Next topic I want to talk about it is um, filters and how we can use the filters to do some signal processing. Basically, filter is the very basics of the time analysis that we will work with that, or sorry, the signal processing that we deal with that. And as I said, very simple example of that is when we are dealing with, for example, the phone. You're talking on the phone, and there is a voice on the phone, and then you want to, for example, cancel the background noise. So you send the whatever you have into some kind of filter in order that that filter let your voice pass through, and then remove the background noise from the signal. So basically, this is what that filter does. Usually, the filter does the same like that. So we give it the signal, and we want part of the signal to be manipulated, or and the part of the signal be just leave it as it is. So as I said, when we're talking on the phone, we want part of the signal that contains the voice of we are talking just be untouched, remain as it is, but the back we want the background noise be removed from the signal. So usually when we are talking about the filters like that, the filters, first of all, I said we can do the filters uh, both in the time domain or in frequency domain. So the filters might be done in both in the time domain or frequency domain. Usually, it's easier to do the filtering in the frequency domain because, for example, if I want to remove some specific frequency in the frequency domain, I just uh, delete that value that is corresponding to that frequency, and that frequency is gone from the whatever signal I have. So for example, here, if I know when I'm talking on the phone and I want to remove the background noise, if I know the frequency of the background noise, I simply go to that frequency and make it zero. Then the background noise is gone and leave the rest untouched. So it can be in time domain, frequency domain. Also, it can be done. We have the uh, analog filtering, or we have the digital filtering. So analog filtering usually is like that. We are using some kind of circuit to do the filter for us. So that circuit does the filtering. But sometimes we use the computer to does the filtering. So in analog filtering is like that. So we have um, some signals coming in whatever equipment we have, and then the circuit does the on filtering for us, and then it gives it out. For example, if we have the amplifier in whatever sound system we have at the home, and you know that we can go ahead and uh, manipulate some of the equalizer on that amplifier. So the amplifier basically, when the signal goes through that, the signal goes through some kind of circuit, and then amplifier manipulated signal, and then it sends it on to the speaker that we can see. But if we play, for example, the MP3 player on our computer, and then we digitally on whatever media player we have on our computer, we change the equalizer on that the media player, then this time it's manipulate the sound that's play from the speaker of our computer, not through I said the board, not through some electronic board, rather than by using some computer programming codes. So it can be done digitally or can be done the analog through the analog. one. Um, so how does it work is that the filter either is analog or is the digital or is in time domain, frequency domain is usual like that. We have something here, assume we call it some kind of, we call it filter, and this filter can be in the time domain or frequency domain, can be analog or digital. And here what we are doing is that we give it we enter a signal, so it's assume that we have the signal enter into that filter, and that filter does whatever we want, and then it gives out the signal out, so leave it out. So for example, if I want to give an example from the analog point of view, assume we have a circuit here. That circuit is a filter that's supposed to do some filtering for us. And then this circuit has two inputs. And then we connect a signal to that input. So for example, I go ahead and say, for example, I connect any type of signal to that input. So connect the input to that signal, to that input of that filter. And then that filter has output that whatever you get from these two output is going to be for example, um, the output. So again, this is how it works. So it's the input and this is the output, and it does some filtering on that. Now, if I go ahead and say, um, um, so for example, assume that I said one thing that filter might does is that assume I have a signal like that. So I would go ahead and say this is a assume I have this is a V in, and I have a signal similar something like that. I have a signal like that, and I see that signal has the one general trend, and also it has some fluctuation around that general trend. Assume I don't want this fluctuation, so if I send it through the filter, so if I filter um, this fluctuation, fluctuations. So filter the fluctuation, what I'm going to get in the output filter is, for example, it's going to be something like that. So there's going to be the V out. And then this, for example, the output would be something look like this. So what is that output? So basically the output is this one that I want. So you can see it here. I have those fluctuations. If I remove those fluctuations, this is what I'm gonna get. So I get this input signal, whatever I have, that contains the general trend and some fluctuation, and then assume I filter out all fluctuation I want. So I have some kind of filter that leave the main trend untouched but remove the fluctuation, and then after it's filtered out, it gives me this as a output. So this is how actually it can work. And as I said, this is what I draw here is in the time domain. It can be done also in the frequency domain as well. So we can remove or manipulate whatever type of signal that we want to manipulate. The next thing about the filter is that the filter has some transfer function. So if I transfer function, So again, in filter, as I said, so we have some, for example, we have some input, and then we have some kind of filter. And then that filter gives us something odd. So we have an input signal, the filter does something on that signal, and then it gets it off. The transfer function is the ratio of this, sorry, transfer function, which is function of, and we write the transfer function in the frequency domain, is the ratio of these two signals in the frequency domain. So if whatever is odd compared to whatever is going in. So if we know the ratio of these two, this is going to be our transfer function. In other words, we can say that the V out, the output signal, is the transfer function times the input signal. So if I know the transfer function of my filter and just multiply it by my input signal, I'm gonna get the output signal that we have. But remember that it is written in the frequency domain. Here, if I want to expand this, what I have is that the V out as a function of X compared to input signal as a function of F. Now I can write it as a phasor. So I can go ahead and say that, okay, this is going to be the the maximum of V max of VM. Let me write it VM so it's much easier. So the maximum of VM for the output signal, which is going to be a function of frequency with the angle of with the phase angle of divided by maximum V that input as a function of F with the angle of F. So assume I have this. So if I do that, I can go ahead and say that the HF is going to be Vm of the output as a function of F divided with the Vm input as a function of F with the angle of, just subtract these two, so angle of theta out function of F minus theta in as a function of frequency. So this, usually we can write that transfer function like that. So why the transfer function is important is that if we know the transfer function, we just simply multiply it by input signal in the frequency domain. So if we have assume we have the transfer function of the filter in the frequency domain, and we have the convert the input signal to the frequency, just simply multiply them. If we multiply them, it's gonna filter the input signal and gives us the filtered signal as an output. Now, if you look at here, this magnitude here is the magnitude of the frequency, is the magnitude of our transfer function. So I can go ahead and say that the magnitude of the transfer function is, so the magnitude of the transfer function is Vm out divided by V in, the maximum of the, or the amplitude of the output divided by amplitude of input, and the the angle of that transfer function or the phase of that transfer function is just theta out minus theta in. Now let's look at how we can use the transfer function to filter the signal. So the first example I want to show that assume we know the magnitude and the phase of the transfer function, and it's going to be like that. So it's going to be is the frequency in hertz and the uh, magnitude of the transfer function here. And assume it's going to look like something like um, this. So it goes from at 1000 it's going to be 3. So at 1000 it's going to be 3, and at 2000 assume it's going to be 2, and at the 0 it's going to be 4. So this is the magnitude of transfer function, and then we have the angle of that transfer function here. Like that. So it's going to be the this time is going to be the angle of that transfer, or the phase of that transfer function, and it's going to be something like that. And so it's going to at 1000 is 30 degrees. So at 1000 it is 30 degrees. So at 0 is 0, and at 2000 it's going to be 60 degrees. So assume we have these two, and what we want to do that is assume we have the input signal, that is input signal in the time domain is going to be 2 cosine 2000 pi t plus 40 degrees. So assume this is what we have, and we want to see if we filter it. So this is the transfer function of filter. If we filter this input signal through these two filters, what is gonna be the output value? So what's gonna be the output signal? So the very first thing is that here what I have here is this is the omega t. So I have the omega t, which is 2000 pi t. So therefore, I know the omega is going to be 2000 pi, and I know the omega is 2 pi t. So the omega is 2 pi f is equal is 2000 pi. So therefore, the frequency for this one, for this wave, the frequency is 1000 hertz. So I know again here, I know the omega. I write it up here. So I know the omega is 2 pi f, or it's going to be 2 pi over t. So this is the omega t. So from here, I know the frequency of this input wave is 1000 hertz. Now I'm going to write this V in as a phasor. So if I go ahead and say, okay, the V input as a phasor is 2, the amplitude, and the angle, which is going to be 40. So this is my input phasor. Now I know that uh, um, the transfer function is V out or V in. So here I'm going to the transfer function. So the frequency is, for this case, the frequency is 1000. So um, H1000. So if I come here, the H1000 has a magnitude of 3 and angle of, so it's 2000, the angle of 30. So H1000 has the magnitude of 3 and angle of 30. So this is the H at 1000. So I'm going to write it here. So it's going to be the H at 1000 has a magnitude of 3, angle of 30 is equal to the V out at 1000. We don't know how much it is. This is what we want to find out. And then we have the input at 1000, which is, we know that's 2 with angle of 40. So therefore, V out at 1000, at the frequency equal to 1000, is going to be 3 with angle of 30 times 2 with angle of 40, which is basically just multiply these two together. So it's going to be 6 and add the angle together again. It's going to be 70. If we do that, so it's going to be the output voltage. And now I can go ahead and convert it back from the frequency. So this is basically frequency. When you write it as a phasor, use it as in a frequency domain. So bring it back from the phasor to the time domain. So the output in the time domain is going to be 6 cosine omega t, which is going to be 2000 pi t, and plus the angle, which is going to be 70. So if this is the input signal, and this is what we have as a transfer function of our um, um, filter, the output signal from that filter is going to be something like that. Now let's look at another example for how we can use the filter if we have more complicated um, cases. So again, assume we have the very same filter here. So I'm just draw it again here. So again, it's going to be the frequency hertz, and it's going to be the magnitude of the filter that we have, and assume it has goes something like this. So at 0 it is 4, at 1000 is 3, and at 2000 it is 2. So assume this is the magnitude of the transfer function of our filter, and then we have the phase or angle of the transfer function of the filter. So go ahead and draw that again, and again this is going to be in hertz, it's a frequency, and this time what we have is the angle of that frequency, sorry, filter transfer function, and assume it's going to be like that. Again, at 0 it is 0, at 1000 it is 30, and at 2000 it is 60 degrees. So now I have it like that. Now this time I assume I have the V, the input signal in the time domain is going to be 3 plus 2 cosine 2000 pi t plus cosine 4000 pi t, sorry, minus 70. So assume this is the input signal, and I want to know that if I pass this input signal through this filter, what's going to be my output signal. So I would say that this time my signal is made of 3 signals. So I would go ahead and say this is going to be the first V in the input signal. This is going to be the second input signal, and this is going to be my third input signal. So I have with similar like that. So I have 3 input signal. They're add together like that. So now I'm gonna just write this input signal, find their frequency first, and second write them as a in the frequency domain or as a phasor. So for the input one, the first one as a time in the time domain is 3. So if you look at it, it's the simple manner. It doesn't change. It doesn't have any sinusoidal format. So it's gonna comes as we call it f1 is equals 0 because there is no sinusoidal wave in that. And remember that when we are talking about this one, when we have the signal with the frequency of 0, also we call it the DC signal, or that's also the mean value in the signal. Just remember that if you hear the DC signal, means the signal that its frequency is 0. So its frequency is 0, and if I write it in the frequency domain or phasor mode, so the V in 1 is just simply 3 with angle of 0. So simply is 3. The second one is 2 cos. It's going to be 2 cosine 2000 pi t. So the omega is 2000 pi. So we know that this is the omega t. So this part is the omega t. So the omega is 2 pi t, which we know the omega is, so this is the omega in the second one. So I write the omega 2 is 2 pi t. You can write it also here. So it's a omega 2t. So, you know, so it's omega 2t. And we know the omega is equal to 2 pi f2. So therefore, the f2 is going to come out as 1000 hertz here. And also, if I write it, this one as a phasor, I know that the V in for the second one is equal to 2 with angle of 0. And then we have the third one, which is the V in 3, which is equal to, So its amplitude is 1, and it's going to be 4000 pi t minus 70. Again, we know that this is the omega t, so this part is the omega 3 t. So therefore, we know that the omega 3 is going to be 4000 pi, which is equal to 2 pi f3. And therefore, if you look at, you cancel out the pi, the f3 is going to come out as 2000 hertz. And the voltage, if I write it in the phasor format or frequency format, the magnitude or the amplitude is 1 and the angle is negative 70. So basically we bring them into the frequency. So the first one has the frequency of 0 with the magnitude of 3. The second one has the frequency of 1000 with magnitude of 2 with angle of 0. And the third one has the frequency of 2000 with magnitude of 1 and the angle of negative 70. Now I will pass each of these two to this filter to see what happens. So if I go ahead, and then I would say here that for the first one, so for V in 1, so we know that the frequency, so let's put it first up there so I don't need to write it. So we know that the filter function is the out divided by h in. So therefore, the h out for each frequency is the filter function for that frequency. Sorry, these are V. So it's a V out divided by V in. Same here. Sorry. Same here. So we know that the output voltage for any given frequency is going to be the HF, this one, times the input signal for that specific frequency. So it's going to be the input one. So now I write it for each of the three solvers. So for V in 1. So I know that the V out of 1 and the frequency for V1 is 0 is equal to HF at 0. So HF at 0 is just 4. So it's going to be 4. And the angle of that at 0 is 0. So it's going to be 4 with angle of 0. So that's the HF. And it's going to be times by V in for the 1. So V in is just 3. So therefore, if I do the calculation, it's just going to be simply just 12. That's all it's going to be for the V1. For input, the second sinusoid that we have, the output of that, the second one has a frequency of 1000. So we have what's the HF at 1000. So the HF at 1000 has a magnitude of 3 with angle of 30. So it's going to be 330. So the HF at 1000, it has a magnitude of 3 with angle of 30. And the input signal for the signal is 2 with angle of 0. It's 2 with angle of 0. So again, if I times these two, so it's a 3 by 2 is going to be 6, and add the angle, which is going to be 60. And then for V input for the third one, what I have is going to be the V out of the third one, which has a frequency of 2000, is the HF at 2000. So at 2000 is going to be 2 with angle of 60. So it's going to be 2 with angle of 60 times the frequency input, which is 1 with angle of negative 70. So it's going to be 1 with angle of negative 70. So it's going to be 2 times 1, which is going to be 2. And the angle is 60 minus 70, which is going to come out as so basically add these two, so 60 plus minus 70, which is comes at negative 10. So now we have this in the frequency domain. Now what I need to do is that I have to go back and convert them to the time domain. So if I go ahead and say, if I convert this one to the time domain, so it's the frequency time domain, the V out for 1 in the time domain is just going to be the same, because the constant is the constant, is not sinusoidal, so it's going to stay the same. This one is the sinusoidal, so V out for the second one would be 6 is the actual cosine. And remember, we have to use the omega t for the second input. So for the omega t for the second input is 2000 pi. So it's going to be 2000 pi t and plus 60. So remember that this is omega 2 t. So we have to use the omega of each one, that the omega corresponded to the input one. The same for the third one, what we have here, I would say that the output of the third over the time would be here 2 cosine the omega t, that omega t should be the same as the input for the input 3. So the input 3, the omega t for the input 3 is the 4000 pi t. So I use the 4000 pi t plus the angle, which is negative 10. So also remember that this one is the omega 3 t. Now that I have them back in the time domain, I can go ahead and add them together. So I can go ahead and say the output would be like that. So the V out is going to be, just add V out 1 plus V out 2 plus V out 3, which is going to be 12 plus 6 cosine 2000 pi t plus 60 plus 2 cosine 4000 pi t minus 10. So it's going to be our output signal. One thing that I want to remember here is that we cannot add them in a phasor when they are in the frequency domain or in the phasor, because they have the different frequency. So we cannot add them together. If they had the same frequency, we could have added them also in the phasor mode, but because they don't have the same frequency, they have different frequency, we have first convert them to the time domain, and then we add them together in the time zone. So make sure that you're not going to add these three together, because although if I write 12 plus 6 angle 16 plus 2 negative 10 is wrong because the omega t is the omega is different for each of them. So that's why we have to first convert them to um, frequency domain, and uh, basically then we do the filtering. So if I want to put it in a simple format, that what we have done here is that when we're doing the filtering, is that when we have the signal, something like that, when we have a signal or whatever signal that we have. So assume I have some simple signal that I have here. If I want to filter that, I will decompose it into, for example, several sinusoidal wave. Assume here it's going to be converted to 2 sinusoidal wave. So like this. So assume it's going to be 2 simple sinusoidal wave, something like this, and then something like that. So, and so this is going to be my ft, and then it's going to be the first sinusoidal wave. So if I go ahead and say this is the v, and it's going to be the input. So this is the input signal, and then I would decompose it to the signal 1 and signal 2. Then what I'm gonna do that I'm gonna here use the filter function. So like that. So I'm gonna say that here after I decompose it, I would say that the V out for the 1 is the filter for the F1 times V in 1 . So also assume this has a frequency of F1 and this has a frequency of F2. And then the same here, I will go ahead and say what I have here, the V out for the second one is the filter at the frequency 2 times the input frequency, the second input frequency. And then when I do that, I would get some types of signal, which again is going to be something like this and this. And assume after it is filtered, for example, this one changed to something like this. And this one, for example, changed to something like this. So assume after filter, it happens also, it's going to be my V output 1. It's going to be V output 2. And then I add these together to get the final one. So I add these together. So if I add them together, it's going to give me the final output signal, something like that, for example. So whatever is my output signal gonna look like, so it's gonna be something like, for example, so whatever I was thoughting that it might be, so assume that's gonna be my output signal. So basically what I've done here, I decompose my original signal to some sinusoidal waves. Then I use the frequency, the transfer function for filter to manipulate each of those sinusoidal wave. And then after I'm done with manipulating them, add them back together to get the output signal. So this is how we use the transfer function or the filter transfer function to get the input signal and then filter it and get the output signal.